Okay, so in chapter 7, we were talking about looking for ranges where we found the standard deviation, and we took the mean from the problem that it gave us to find those ranges. So we said that the mean they gave us was going to be the same as the sample mean that we're going to use in the calculations. What happens if they don't give me the mean? We're going to find it, right? So we're going to find it from a sample, not necessarily the population. So is that mean going to be totally accurate? No. It could be close, and that's what we're going to look at today. We're going to start looking at how to find, when we find the mean, figure out what's known as our confidence interval. It's like we believe it's going to be within this range. We don't know exactly where it is, but we know we're going to be 90% or 95% confident that it's within this range. So you're going to notice a lot of the calculations and stuff we're going to do, basically the same thing we've been doing before. All right, nothing's really drastically changed here. All right, so we've got a sample of 36 new homes. So those are the prices in thousands of dollars. And so they're mobile homes, which means that they're a little cheaper. I'm like, look, that'd be really nice to have houses that cheap. Those would be tiny houses nowadays. Notice how they changed the name. It's no longer a mobile home park. It's a tiny home park. It makes it sound better. It's like they're the same thing. All right, so we found our mean. I didn't make you do it, as I'm pretty sure everybody in here knows how to find mean at this point. So notice the symbols. So that symbol, remember the X with the little line over it? That is known as my sample mean. And we're going to use that. It's going to be called a point estimate. So when you hear point estimate, that's what it's talking about. It's an estimated value. All right. I don't know. That's just one sample that I've taken. So that's what we're talking about, a point estimate. If I've done multiple ones, I could have multiple points. But in this case, I have 1 point estimate. So for this one, they sampled the houses. My mean was 63.28 thousand. All right. So a point estimate's a parameter is the value of a statistic used to estimate the parameter. So it's basically just an estimate. That's why it's called a point estimate. It's just another little definition, something that if you see it in the problem or hear about it, now you know what it means. But like I said, it's not much different than what we've already been talking about and doing. So, all right. So what's the other piece of information I need to know? We have our mean. We need the standard deviation. We're going to talk about on Thursday what happens if I don't have my standard deviation, how we're going to do that. Because, again, when we're looking at a whole population, it's really hard. Like, we would need that information ahead of time. And a lot of times, you're not going to have that because we're looking at, like, we have our sample, we have a little bit of data, but we really don't know what's going on with the whole population. We're trying to figure that out. All right. So we're starting off with, well, now we don't have the mean. And then we'll move into, well, what happens if we don't have the standard deviation either? So how do we figure these things out? So for this one, let's assume we had a standard deviation of $7,200. So 7.2 thousand. So let's start identifying some information. So we've got our sample mean. We had that already, and that was, what was it, 63.28. And now we know our standard deviation is 72 or 7.2. So we want to show that 95% of all samples of 36 new homes are from that interval. So 95%. So if we're going to go look at my standard deviation table or my Z table, we want to figure out where that 95% falls. Okay. We want 95% in the middle, right? So what's the value that I'm looking at my Z table for? So remember, we want like basically this value down here and this value down here. If I want 95% in the middle, what's going to be on each side? Not 5%. It's 2.5%. And 2.5% up there. Remember that the negative side and the positive side are the same. So if I find the negative one, which will give me this side, I can just make it positive for the other one. So I don't necessarily have to do the other piece. So let's look at our Z table. So if you have your Z table, you can take it out. I'll put it up on the board in a second. If you want to come grab one, because I gave them out during the test. You want to come grab one? Or do you have a Z table? Yeah. Okay. I gave them during the test, so we pulled up the paper. So, all right. So we're looking for 2.5%, which would be 0.025. So we're scrolling down. Or point. Yeah. Is 1.96. Hold on a second. They used a different number, and I'm not sure why. Oh. We skipped a step as well. I jumped ahead. We'll do that in a second. But yes, we did all that right. It is 1.96. I just jumped to one. I jumped ahead of the book. All right. We do have to do one thing for the standard deviation, though. It's not 7.2 for the sample. What is it for the sample? It was 7.2 divided by the square root of 36. So in this case, it's 1.2. They did it slower than I was doing it, which is fine. So 95%, if we're looking at the empirical rule, was 2 standard deviations, right? Which we just found the exact one was negative one, or was 1.96, right? But that's still pretty close to the 2 standard deviations. So that's why they did the plus or minus 2.4, because it's 2 times the standard deviation, which was 1.2. Okay. So if I'm going to add and subtract that, so we had 95% confident. I think I actually put that there. Yes, I did. So our mean was 63,028. So they minus 2.4. They minus 2,400 to get that one. And they added 2,400 to get that one. So I know that my mean is 95% sure that's somewhere between 60,880 and 65,680. That the actual population mean is somewhere between. Okay. I don't know that it's exactly 63,280. It could be. That is a possibility. But I'm 95% sure it's somewhere between there. Okay. So that's when we're starting to talk about those confidence intervals. Is figuring out where it is on either side of it. Yes.
Now, how would we figure out the other 5% of that?
You're never going to get 100%. Because, so in essence, if you want 100%, you know the mean is somewhere between 0 and 1 billion.
No way.
No, but that's what I'm saying. That's 100% means you basically want everything. You're never going to get to 100%. That's why if you look at the standard deviation curve, it kind of tails off, but it never actually gets there. Actually, if you looked at the table that I gave you on the side, you can actually see it's got the 5 standard deviation. It's 0.99999999713. It's still not 100%, even at 5 standard deviations out. So that's where you can get really, really close, but you can never get the total amount. You're never going to be able to figure out exactly what the population mean is unless you add up all of the data to do. So if you took every single household in the entire, or in this case, mobile homes in the entire United States and added it up, then you'd have the population mean, and you'd be able to figure that part out. And you'd be basically at that point as close to 100% confident as you can be because you've done it all. But that takes a lot of time, a lot of money, a lot of effort. All right. When we're looking at things, we don't necessarily need that amount of precision. If we're within, in this case, $4,800 of the actual mean, that's reasonable. It's like if we're talking about houses, you're basically, even if we round it up and say within $5,000 of the actual mean, that's pretty good. Before we end class tonight or today, I'm going to actually show you how to figure out if you want a specific error amount, how many people you'd have to survey or what number that you'd have to get to get that amount of error correction, basically. Okay, does that answer your question?
Yes, that pretty much is my question.
Okay,
thank you.
No problem. All right, so a couple more terms that we're going to need to know. You heard me mention confidence interval. A confidence interval is the interval of number of obtained from a point estimate parameter. So basically, I took my point estimate, and I know it's within this range. The confidence level is how sure I am of that amount. So in the problem we just did, we were 95% sure. That's going to be my confidence level. Okay. And then confidence interval estimate is just the range that we're looking at. So we can change that 95%. You'll see everything from 80 to 99.9%. All right. So it just depends on how accurate you want your information. And what we're going to notice is the more accurate you, the higher higher confidence level you want, the wider that range is going to be. So we might need more values to get it to be closer. So again, money, effort, time. It's like those things come into play. The more calculations you have to do, the more you need. And that's why a lot of companies and stuff now are moving towards what's known as big data and AI, because computers can do these calculations a lot faster than we can. So they're using huge data sets to be able to do these calculations, to be able to a lot more confident in their information. Okay. It's like I remember when I worked at the bank in the 1990s, we were doing escrow analysis, basically figuring out how much money you're paying for taxes and stuff like that. And the bank was happy if at the end they paid out all the amounts and everything else. If they were within $1,000 of the actual amount that they paid out, they were fine. They were happy with that. They were happy with being off $1,000. Okay. By the end, when I left, so that was in 95. When I left in 99, or just after there, with the programs and stuff that I wrote, we were down to within $1 of it. And it was literally just being able to use the computers and the power to actually be able to analyze and figure out the values and to back check when people are typing numbers in. So it's like, it's a matter of the more information you have, the better, more accuracy you can get. And that's just one place of saving a lot of money. So, all right. It's called the one mean Z interval procedure because you could have multiple ones. We will not deal with multiple ones here. We're just going to deal with one. So, a few things that you need to look at before we can do this. Okay. We need to make sure that the sample that we have is a random sample. Okay. So there can't be any bias in how we've collected the data. It's got to be randomized. That's key. We need to know that it's a normal population or a large sample. What's the number that I said makes a large sample? 30. All right, as crazy as it sounds, that 30 doesn't seem like it's that large. Once you get past 30, it's pretty much a normal sample. We need to know our standard deviation. Okay. And one other thing that they didn't put there is when you're looking at your data, you don't want any major outliers. Okay, so when you're looking at it, if it's close, it's fine. But like, say we were looking at those mobile homes, the prices there, I think they went from like 40,000 to like 80,000. Say you had one that was $340,000. That one's going to skew that data a little bit. So what you do is you would eliminate the outliers and recalculate based on the ones that were within the range that you had. So if we had one that was 340,000, we would just cut that one off and we would use 35 numbers instead of 36. I wouldn't go out and find another one because then that wouldn't make it random at that point. So I would just look at the one less piece of data. Okay. Because the goal is you're looking for something that's going to help us. It's like those outliers can skew that information quite a bit. All right. So for our confidence level, it's 1 minus whatever my A is. So in this case, if it's like the 95% or whatever else, that's where we figure out my confidence level. And you'll notice that it's the Z. So A divided by 2. So in this case, for 95%, if we did 95% confidence interval, it'd be 0.05 divided by 2, which is the Z 0.025. Okay, remember that number is the number that I'm looking for at the right, which basically we just did a little bit ago, and we came up with that was the 1.96. I remember, since it's symmetrical, you can just look at the negative version of it, look for that number, and then just change it to a positive. You have both. Okay, so you don't necessarily have to remember, okay, let me subtract to get it to 99.75 and find, or 975 and find that one. Just look for the negative side and you take care of it. Because you're going to do both of them anyway. Now, to find our confidence level, so we're going to take our mean and we're going to add or subtract whatever this value is. So the Z A over 2 times my standard deviation of the sample. So for the one we just did a little bit ago, or for the one we did, it would be 63 point, what was it? It was 63.8, right? Hold on. 28. 63.28 plus or minus, and it was 1.96 times 1.2. That's how I figured out that 95%. So whatever the mean is, plus or minus the z-score that we got for whatever confidence interval I'm looking for times my standard deviation for that sample. And that's going to give me my confidence interval. Any questions on this procedure? I know it sounds really complicated and all these steps and everything else, but
What is it? What does that say before the 2? Z.
A2, A. It's the,
Looks like a 9.
I know, because I dragged it out. It's an A.
Okay, so Z with the A over 2 times standard deviation of
Standard deviation
square
is a
root
sample.
of the sample.
Yeah. Okay. All right. So let's look at this. Let's look at 8.4. So first thing we have to look at is, let's look at, make sure my assumptions are met for this one. So remember my assumptions: random sample, normal population or a large sample. I have my standard deviation, and I don't have any major outliers in the problem. All right, so in this problem, I'm looking at 50 people. And it says they are randomly selected. Okay, and I've got my standard deviation of 12.1 years. So we've got 50 people. Is that a large enough sample? Yep. Is it randomly selected? Yep. And we have the standard deviation of 12.1, correct? Okay. Let's look at the actual data real quick and make sure that the data that they gave us is there's no major outliers or anything else in it. So if we're looking down, these are ages of people. So we're looking at like 16, looks like the youngest. Yeah, we're going up into like 70. Nothing seems really strange out of there. Like we don't have a 110-year-old person working or a 2-year-old, things like that. So we don't have anything really strange there. So there's no real outliers. And actually, they did a nice little chart. And remember, you can see it's the 1.5 times your interquartile range gives you your official outliers. Most of the time, you can look and pick them out. You don't really necessarily have to do a box and whisker plot. If you're using a computer and stuff like that, it makes your life a lot easier, and you can do that. All right, so it meets the criteria. All right, so let's find our 95% confidence interval for this. So step 1, we need to do what? What's the first thing I need to do? I need my mean, right? And we need to find our z-score. So, but let's find our mean. Well, I'm going to give you the mean. Let's find the mean first. What was the mean for this one? The mean is 41.4 years old. So my mean is 41.4. And now we're going to look for my standard deviation. Is the standard deviation of the thing, so 12.1 divided by the square root of 50. So what is my standard deviation for this one? Uh, 1.71. Okay. Now, here is the nice thing about confidence intervals. You're typically going to use the same ones a lot. We already looked up 95%, correct? What was the z-score for 95%? It was plus or minus 1.96. Okay. I would have that written down in your Z table. 95%, 1.96. This way you don't have to keep looking it up. And actually, depending on the Z table, some of them already had them on the side. The one I printed out didn't have it on the side. But having those numbers, it saves you having to look them back up again. Okay, because there's only going to be a certain number of them we're going to use. Like I'm never going to ask you for 96.5% confidence interval, right? It's just not going to happen. So it's going to be ones that are regular. 95 is one that's used a ton. 99 is used a ton. So those are two that you're going to see quite often. So we've got this one. It's plus or minus 1.96. All right. So now I can figure out my confidence interval. So I'm just going to take my 1.96 and multiply it by the 1.71. And we get 3.35. And then we do the 41.4 plus or minus that. We get 38.05 to 44.75. To 44. And we're 95% confident that it falls somewhere between those two values. Does that make sense? Does the process make sense? Okay. So you see, a lot of the stuff, we've actually done this stuff. We were doing that stuff before. It was just a matter of now we're looking at it in terms of a little more how we would actually use it. So. All right. The next thing they're looking for, you look for this quite often, is called the margin of error. If you notice, it's the same thing we just did. So for the problem that we just did, my error is the 1.96 times the 1.71, which was 3.35. That's my error. That's my margin of error. It's plus or minus 3.35. Okay. We talked about this when we were looking at polls. That's where that plus or minus 3% comes in down the bottom of your polls all the time. That's how confident they are in that. They're 95% confident that they're within 3%. All right. So we did the margin of error for 95%. That was plus or minus 3.35. I want you to do the same thing for 90%. Okay, so I'll give you the few numbers that we had. So the mean was, what was it, 41? What did I say it was? 41.4. And then my standard deviation was 1.71. All right, so do the same thing you're doing it for 90% this time. All right, what's my so 95% was 1.96. What's 90%? What's the Z-score for 90%? 1.29. What number did you look up? What should you have looked up? 0.05. Remember, you have to cut it in half. So we're looking for 0.05 or 0.95 if you were going that direction. And you should have gotten, it's right between 1.64 and 1.65. So the number they typically will use is 1.645. Okay. So if you want to write down on your thing, 90% is 1.645. If you use 1.64 or 1.65, it doesn't make that big of a difference. But again, they typically use 1.645 because it's right in the middle of those two values. All right, so what's the margin of error for the 90%? So we're just going to take that number and multiply it by the 1.71, right? So you should have gotten 2.81. Or right around there. All right, so what are some things you notice? So the actual confidence interval is, well, I'll get the actual numbers, but it's fine. It doesn't make much difference. I think you guys can add and subtract that pretty easily. What are some things you notice? So we went to a 90% confidence interval. What happened to the, yeah. Okay, does that make sense? Okay. Is that a good thing or a bad thing? Okay. Are we more confident that it's in between those numbers or less confident? We're less confident. We're now at 90% confidence instead of 95% confidence, right? So if I was to do this 100 times, 10 of them would be outside of that range on average. Where the first one, only 5 of them would be outside of that average. Now, honestly, in this situation, it might not make that big of a deal. All right. We're looking at age of the people working. Somewhere right around 3. That's probably not a horrible margin of error. Okay. But yes, the range is smaller, but we're less confident that it's going to be in there. So it just depends on how accurate you need your data. Okay. All right. So it does make sense that it's going to be shrinking in that situation. Just some of the little things to look at. All right. Let's do the same thing. Similar thing. We did the 95% confidence interval was the plus or minus 3.38 or 3.35. And we have our mean was 41.4. They want you to do, actually, we don't have our mean changed for that one. So our mean for this one was 41.4, and my standard deviation was 1.71. They want you to do the same type of data, but this time they did a random sample of 200 people. So we've got a new mean. Our mean is now, for this one, 42.2. Are we going to have a new standard deviation? Yep. So find my new standard deviation. So the original standard deviation, if you don't remember it, was 12.1 years. Because you did need that. And they didn't put that back in this thing. So my new standard deviation, 12.1 divided by the square root of 200 is what? I got 0.8555. It kept going 5 to 0.86. All right. So find my confidence interval for this data. Remember the z score of the 0.025 was 1.96. So I got plus or minus 1.69. Okay. So what do we notice about these two confidence intervals? Is the new confidence interval smaller or bigger? It's smaller. Did we change the 95%? No. What do we change in this problem? We looked at more people, right? We increased our sample size. Okay. So looking at the two problems we just did, which ways do we have to decrease the margin of error? What are my two options? Yes.
Increase sample size or increase your confidence.
Right. Or my confidence level, yeah. So I can either decrease my confidence or increase my sample. Either one of those will lower my margin of error. Okay. So for a fixed sample size, decreasing the confidence level will decrease the margin of error. And for a fixed confidence level, increasing the sample size will decrease the margin of error. Both of those will improve the accuracy of the confidence interval estimate. Just depending on, again, the data that you're looking at. If we need to keep a specific level of confidence, we want to stay at the 95% and I want to lower it, I need more people. If it doesn't make much of a difference, if I can go down my confidence level a little bit and we're still going to be fine, go down with that and you can save yourself some work and having to find more people. So what do you think is the next step? We're not getting rid of standard deviation today. We're doing that Thursday. What would you want to know before you went out and did your study? What would be the piece that you'd like to know? Could you figure out your margin of error before you went out and did any work? No. What information do I need to know ahead of time in this problem? What's the pieces of information that I need to know? I need to know my sample size. What else did I need to know? Mean of my sample, right? But they didn't have to tell me that. That's what I'm getting, correct? Okay. I needed to be a random sample, and I needed to have my standard deviation, right? So if I tell you, so let's think about this. Let's look at this for a second. My error formula right here. So let's make this a little bigger. This error formula. What pieces of information do I need to do this? I need my z-score, which we make up, right? We're choosing that. Okay, we're choosing the 95% or the 90% or the 99%. We're choosing that number. So that's not something that I need to go out and find. That's something that I have before I even do the work. The standard deviation, which again, I have to, in this situation that we're working on right now, you have to have that before you go out and do your stuff, right? Okay. And then my sample number, right? So if I wanted to do this the other direction, if I wanted to say, I want my error to be within 1 year, okay, at a 95% confidence interval. Could we figure out what the n needs to be for that? Yeah, think about, I know, go back to your algebra classes. As long as I only have one thing I'm missing, right, I can solve for that. So what a lot of times happens, this goes back to where I was saying before, remember the whole like 1,000 or 2,000 people you survey and get the information? Is anywhere in what I've been talking about the population size? No. Right? We haven't talked about, in anything we've talked about today, we haven't mentioned once the population size. All right? We've talked about our sample size. We've talked about the population standard deviation. We've talked about the mean of my sample. So, in essence, it doesn't matter if I'm talking about 10,000 people or 10,000 homes or 300 million homes. Neither one of those matter, which sounds really strange that doesn't matter. Okay? Because of the way we do the statistics and because of the calculations and how it all works, that number doesn't make a difference. All that matters is that it's normal, it's normally distributed, which most groups are once you get to that size. And in this case, we have the standard deviation. Thursday, we'll change that and we'll play around with something else. All right. So here's the formula to figure out our error or our number of people that we need to look at. So this formula looks crazy, but it's actually pretty simple. This right there, my Z A over 2, that's the number that we were looking for. So for 95%, it's 1.96. For 90%, it's 1.645. What's 99%? Because that number is going to come up quite a bit too. Let's look for the 99% one. So we're going to be looking for 0.005, right? Oh, wait, no, not 0.005. Yes, 0.005 because it's 1%. So we get 2.575. So we look here, I'll show you. So we're looking for the 0.005, which is right between the 0.0051 and 0.0049. So we get 2.57, and then it sets us right in the middle. I just split it in half, 7.5. So we've got our Z number. We don't even, if you have those three written down, unless they give you something crazy, you don't even have to look at your Z table. We have those numbers. Those are the three we're going to use. So we've got that. We need to know our standard deviation. So for the problem that we just did, my standard deviation was 12.1. That did not look like a 6. So that was 12.1. And let's figure out, I want an error 1 year. So my error is going to be 1. So if we look at this formula, we have, we're going to do 95%. So 1.96 times the 12.1. And we're dividing it by 1. And then we're squaring. So there's my formula. So I would need to get the ages of 562 people. And this problem was looking at original, let's see, if I go back to the original problem, It says the Bureau of Labor Statistics collects information on the ages of people in the civilian labor force. So this problem is talking about looking at every single person that's working in the United States. And if I pick a random sampling of 563 people, because I can't pick 0.4 people, so you always go one more. So 563 people, I can be 95% sure that I'm within 1 year of the actual age of the entire 165 million people that are working. What if I wanted to change it to half a year? We would just change that bottom number to 0.5. So I would need to survey 2,250 people. And I'd be within a half a year, plus or minus, which is actually 1 year total, right? I'd be within 1 year total of the actual mean, like a half on both sides. Okay. That's how the pollsters only have to call a couple thousand people and be able to figure out what everybody in the country thinks. So then why do they get it wrong all the time? People lie. What else? Huh? Right. What's one of the assumptions we make? Yes. Yes. It's a random sample. Right. So when they are looking at it, one of the major assumptions we make is that it has to be a random sample. When you're doing phone surveys or internet surveys and stuff like that, there's built-in bias. It's not totally random. That's where they start to make their errors. They try their utter best to get as a random sample as possible. But humans aren't always random. When we're looking at data like we were talking about this, the statistics and stuff like that, the labor force, we have that data. All right. So they're just randomly picking out some people. It was like they don't need to necessarily, like, that is easy enough to get a random sample of that information. So our data that we have, we can assume is pretty darn accurate. Okay. All right. We're done. Thursday, we'll add in how to find this if we don't have a standard deviation, which is key to all the stuff we've done so far. So, like, we don't have that. Something's got to change.
Professor, you just hand back that.